What is up, everybody? Welcome to the chapter 3 review. Let's get started. I'm not even going to do anything with this. We want to get through this quick. So today we are going to be going through the logarithmic, exponential, and a logistic model. And then we have our first function. I should stop doing these designs. I really should. The next one's evil. So e to the x is our first function. Now e to the x is a special function, because whenever you put 1, 2, 3, 4, it grows super fast. It grows e times faster every single time you put the 0, 1, 2, 3, 4, the next term next to it. It grows e times faster. Here are all the transformations. I think it's kind of obvious. It has a horizontal asymptote at the y equals 0. Limit as x approaches negative infinity is 0, and limit as x approaches infinity is infinity. Other than that, it isn't really that much special. It isn't negative unless if you make it negative. This will have the whole range as negative. Meanwhile, this will have the whole range of decay. So I'll tell you what that is later. So let's graph e to the x, right? I already graphed e to the x pretty much. So we're gonna have 3 points. We're gonna need 3 points. We're gonna need this 1 point right here. I'm gonna put 2 right here, and I'm gonna put 3 right here. And if you're wondering what e is limit as x approaches infinity 1 plus 1 over x to the x power, which is about this much. Basically, when you're taking a when you're compounding interest, when you're compounding interest, 100% interest, which is really nice, and you compound it forever and ever and ever, you'll get that much. You'll get that much times your money per year. So if you have $400 and it's compounding continuously at 100% interest, at the end of the year you'll have 400 dollars, right? 400 times dollars, which is a lot of money, like a high increase in money, right? So we'll graph this exponential function. We're gonna need 3 points, and our 3 points that we need is normally 0, 1, and -1, unless in special circumstances it's not. They all pass 0, 1. All of these graphs pass 0, 1. Even this one that looks weird, right? And then we have as x equals 1. This is e to the -1. That's 1 over e. So it's just smaller. Oh god, smaller. So it'll be probably like right here or something. Probably a little lower. It'll be probably right like here, right? And then e to the 1 is just e. E is about 2.718, so you just put that right here and you can draw your graph. Something like that. That's a bad graph, but whatever. 2 to the x. What is 2 to the x different from e to the x? It's basically e to the x, but less. It grows less fast, right? So 2 to the x is, if you have 2 to the -1, it's 1/2. No, 2 to the -1. Okay, 2 to the -1, it's 1/2. It's not -1/2, it's 1/2. And then we have 2 to the first power is 2. So it will be, let me get a different color. 2 right there, and then 1/2 right there. So it will be, oh god, okay, let me make, you know what, whatever. Let me make this, oh god, I'm sorry. I want to show that this grows less fast. There you go. It's something like that, right? What about 1/3 to the x? 1/3 to the x is, if you've noticed, this is 3. This is actually 3 to the -1 to the x, which is 3 to the -x, right? This is 3 to the -x. So if you put 1 in there, you will have the 1/3. So when x equals 1, it's 1/3. And then when x equals -1 is 3, because -1 is 3. No, -1 is 1, so 3 to the 1 is 3. So then you'll have something like this instead, right? They all pass 0, 1, because if you put it as 0, it'll be 0. So you'll have something like this instead, right? So that's the 1/3. That's the 2, and then the bottom the, right? I just put different colors so you know which one's the 2, which one's the, and which one's the 1/3. The 1/3 grows. The 1/3 is called exponential decay. Now e to the negative x. If you have e to the negative x right here, and you would graph it, it would look like this. Basically, it would just look like this. It wouldn't go up as you have higher values. It will go down as you have higher values. In the other direction, it will go up exponentially. So next is the logistic function. The logistic function is like this. Basically, whenever you have a population or a virus, like we have the coronavirus right now, it can only spread to a certain extent. There's only a maximum capacity that it can spread to. Right now, we have about 7 billion people in the world. So 7.6 roughly billion people in the world. So we have to, let me pull up a calculator. So we have to try to limit the spread of the coronavirus. We have to make this lower, as low as possible, basically. The lower it is, the better it is. And the lower this cap is the highest amount of people that can be infected, or the most amount of people that can be infected. And it goes fastest in the middle, and then it tapers off at the end, which is basically the same as our coronavirus growth. If you look at some of the graphs in, I don't know, Vietnam, or if you look at some of the graphs in South Korea, or Taiwan, or Japan, or those types of countries where they've gotten it covered, or China, right? You'll see a logistic graph, which looks something like this. We'll see the features later. The reason why I explained the features of e to the x in the beginning was because you've already known all of it. But this is all the transformations that will happen. They're all unique. It's not an even or an odd function, so they're all unique, right? So, features of the exponential. I'll be going through this really quick because you should have already known this. So, a is the initial value. It means 0 when x is 0, y is a, right? And then b is the multiplier. So, any exponential function, the previous term is 1. No. Okay, this is wrong. I'm sorry. The term is 1 b times the previous term, right? So the exponential function divided by common ratio. This is the exponential for 2 times 3 to the x, because 0, the initial value is 2, and then times 3 every time. This one, this one's the same graph as this one. The initial value is 2, and it times 3 to get 1 comma 6. And in general, this is the graph. I don't really like this because it's cool, but it doesn't actually explain anything. It's basically just, you start from 0, you divide by b every single time, you go to the negative, and you times by b every single time you go to positive. So which of these are exponential functions? Well, it doesn't matter if it's of x or y, they can still be a function, but we're just going to see which ones are exponential functions. This one is an exponential function because it's 4 to the x. This one is debatable. Before I did this chapter, I would say this is an exponential function, but it's not an exponential function, as in it doesn't clearly state that it's an exponential function in the book, because 2 to the x plus 5 is a translation of 2 to the x. It's not necessarily, there's no initial value, there's no base value, it's a translation of 2 to the x. So I'd say for the time being, this is not an exponential function, but it does grow exponentially. So for me, in my opinion, it is an exponential function. In the book, it doesn't say that it's an exponential function, so I can't guarantee that it's an exponential function. G is an exponential function. H is an exponential function because minus, and then you have 3 to the minus x, which is minus 1/3 to the n, which is exponential, right? It's just the other way around. A to the x plus b to the c. A times x plus b to the c. This is not an exponent. This is 100% not an exponential function, and the reason is x is at the bottom, right? It's like x squared. X squared is not exponential; it's polynomial. X has to be at the exponent for it to be exponential. This one is not as well, because x is both at the bottom and at the top. If x is at the bottom, it's not an exponential. This is very, it's there. There's no category to specify what this is, right? But it's not an exponential. Determine the formula. What's the initial value for this? The initial value is, well, let's do f of x is equal to, the initial value is minus 6 times, and then how much do you have from 18 to 6? That's, you times it by 1/3, and then this one you times it by 1/3, and this one you times it by 1/3. So the formula is negative 6 times 1/3 to the x, or negative 6 times 3 to the negative x. They both work. Next, determine a formula. Now this is a little bit harder because I didn't tell you two of the numbers. First of all, our initial value is 1, so we can just do that, right? Our initial value is 1. We have h of x, so we know that we have to multiply by something 3 times to get to the 1. So multiply, right? Multiply, let's say b, so b and b. We have to multiply by something 3 times to get to 1. So we can actually figure that out, because we can just do 27 over 64 times b to the third power is equal to 1. And then we can multiply by 64 over 27 both sides. B to the third is 64 over 27. And then take the cube root, and this is a very nice number because it comes out to 4 over 3. 4 over 3. So then our formula, let me see if it even fits in the, yeah, okay. So our formula is h of x, initial value is 1, so we can just remove the 1. It doesn't even matter. 4 to the third x power, right? There's no extra line in here, I'm sorry. 4 to the x, 4/3 to the x. Determine a formula for the exponential functions. This is 12.5. Okay, so we do the exact same thing, basically. We have this 0 right here, and then we have 2. So this is 0, this is 1, this is 2. Oh god, that's a really bad one. This is 0, this is 1, and this is 2. We already have our initial value, it's 2, right? So it's, this is, let's say g of x is equal to 2 times something. What's the something? Well, we have 2 times b times b. So 2 times b squared is equal to 12.5. So b squared is 6.25. And if you work that out, b is equal to 2.5. In this context, b is equal to 2.5. It might be negative in other contexts, but it's not in this, because it's increasing, right? So it'll be g of x is equal to 2 times 2.5 to the x power. This, we don't have the initial value, but we can do the exact same thing, right? Minus 3, 9, and 1, 1, 9. So we have minus 3 to 1. We have to multiply by something 4 times, right? We have b, 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 b. So minus 3 to, we have to multiply by something 4 times. We have 9 multiplied by b to the 4th gives you 1/9. So what do? You multiply by 1/9 on both sides. You have b to the 4th is 1 over 81. And then b is equal to 1/3. B is equal to 1/3. It can't be negative because I would just flip the thing over. So it's 1/3. It lowers the thing down every single time by 1/3. So with this 1/3, we can calculate our initial value. We can basically calculate our initial value. We have y is equal to a times 1/3 of x. Y is equal to a times 1/3 of x. And then we can put one of our points in. I'm going to put 1 and 1/9. So 1 and then 1/9. We'll have 1/9 is equal to a times 1/3. Multiply by 3 on both sides. A is equal to 1/3. So then our equation, I'll just put this in this color. Our equation is, let's say, L of x is equal to 1/3 times 1/3 to the x. Right, that's our equation. 1/3 times 1/3 to the x. Or 1/3 to the x plus 1. Right, that works as well. Next slide. Okay, our next slide is, I think it's still exponential. Yeah, so I already pretty much explained to you, so we can pretty much just skip this slide, but exponential growth is when you go up, it'll be of the form it'll be of the form a times b to the x, and exponential decay is a times b to the minus x, or a times 1 over b to the x. Or in this case, it might make you write in the term, which I think I've explained in I explained in the next slide, a to the e kx, like this, right? But you just gotta make sure that you know that this e to the k right here is equal to b, and when b is less than 1, then it'll decay. When b is higher than 1, it'll grow. When b is equal to 1, it's a linear function. When b is equal to, actually no, when b is equal to 1, it's a constant function, so it's just straight line, right? E to the k x is equal to b, and I think I have it in this slide. No, I actually don't. So if you ever have this form a e to the kx, when this k is less than 0, so form, I'm gonna write it right here, a e to the kx, right? When k is less than 0, it's exponential decay, because then it will be a to the power of 1 over whatever, and our 1 over whatever is decay. If k is higher than a 0, it's a growth, and if k is 0, then it's a constant function, right? So k is higher than 0, it'll be like a to the 1.02 to the x. It'll still grow, even though it's a slow growth. When k is smaller than 0, even though it might be a small decay, or not a decay at all, it'll be, even though it's a small decay, it'll still decay, right? So there you go. Transform f of x into the following functions. We just use our function transformations. I don't even think I'm gonna do 57 and 58 3.1. I'll do 58 3.1. I won't do 57. So 3 to the x is 3 to the x plus 5. This should be pretty much self-explanatory by now. 3 to the x, 3 to the x plus 5, x plus 5 needs minus 5 to shift it back to 3 to the x, therefore it's a left 5 shift. E to the x, minus 2 times e to the minus x, e to the minus x. The minus x is automatically a shift, a reflection across the y. So reflect y, right? Reflect across the y. Oh my god, I'm really sorry about the lag. Reflect across the y, and then after you reflect across the y, there's a 2, and then there's a minus. The minus means reflect x. So you reflect y and you reflect x, and then after that you vertical stretch to vertical 2. 0.2 tx, 0.26 minus 2x plus 8. So this 6 minus 2x, it'll actually be very wise to just take the minus 2 out of the 6, so we can just factor it. In fact, that's what you have to do. So 0.2 to the power, so we're gonna change this to minus 2x plus 6. So it'll be minus 2 times x minus 3 plus 8. Okay, let me write that down again. 0.2 minus 2 x minus 3 plus 8. I'm really sorry for the ugly. Yeah, but if you see that function, if you see this function, you will see that it is plus 3, so 3 right, and then there's 2 on here, so it's 2 horizontal, 2 times horizontal, no, not 2 times horizontal, I mean 1/2 times horizontal, 1/2 times horizontal shrink. You see the negative, so it'll be y reflect, and then you see the 8, so it'll be 8 up. Right? 8 is outside of the function, so it'll be 8 up. Which two of these are identical? First of all, we have so you see these are 2. You see there's a lot of 2's in here, so let's do it in terms of the 2's. So y1, what's y1? y1 is 4 times 3x minus 2, which is 2 squared 3x minus 2, which is 6x minus 4, right? What's our second one? 2 times 2, 3x minus 2. It will be 2 to the 1 times 2, 3x minus 2. And since it's 2 to the 1 here, you can add them together. 1 plus 3x minus 2. And 1 plus minus 2 is just minus 1. So 2 to 3x minus 1. And then, oh, you see, y3. 2 to the 3x minus 1. Same thing as y2. If you simplify this y2, you have 2 to the 3x minus 1. So these two are equal to each other. And that's it. Now let's do 58 3.1. Okay, it's only, I think it's already been 25 minutes. It's 21 minutes. So it's we have our 3.1. Let me go all the way back to, and we have page, no, we don't have page, we have question 58. So question 58 is carbon dating. The amount of substance, C grams of carbon-14 present in a certain substance is 20 to the minus 0.00001216 T. What was the initial amount of carbon-14 present? Well, the initial amount is the initial value. What's the initial value? Wait, this is 20e to the power of minus, not 20 to the power of minus. So the initial value is just 20, right? It's our 20. B. How much is left after 10,400 years? We can put that into time. I'm going to use my calculator right now. It will be 20 times e to the power of 20 times e. I can't actually put e in here. What the heck? Okay, I'll just put the real number then. 2.718 to the power of... Okay, this calculator is trash. I'm sorry. 20 times 2.718 to the power of minus 0.00011216. 20 times 2.718 to the power of minus 0.00001216, and then that is multiplied by the 10,400. So there will be roughly no internet. There will be no internet. I'm really sorry. I'm truly sorry. Okay, I'll probably just move on to the next ones until this internet shit works. Let's reset this. I'll move on to the next slide. Okay, so you'll have to wait for me. I'm sorry. Okay, we'll have our next slide, I think, is logistic functions, but active inspire doesn't want to work right now. So okay, actually I have my result now. It's 17.6 grams. So okay, active inspire works now. Great. So this is our 5th grant. Our are 17.6 grams, right? And I'm not going to do the second question, it's going to take too long. End behavior, this is our next function. This is basically our logistic function right here. So what's the end behavior of this function, and what's the y-intercept of this function? I should have said b over 1 plus k times minus e to the minus x, but whatever. End behavior of a function. The end behavior of this, well, let's see. If you put negative infinity, okay, this is the function that I actually wanted to see. So if we put negative in, so focus on this, don't focus on this. If we put negative infinity in here, limit as x approaches negative infinity, you will get e to the infinity, which is infinity. So the whole bottom will be infinity, therefore the whole thing will just be 0. Right? The whole thing would just be 0. What about if you put limit as x approaches positive infinity? Well, if you put limit as x approaches positive infinity, you'll get 1 over e to the infinity. And 1 over e to the infinity is just 0, basically, because 1 over infinity is 0. Multiply by k, you'll still get 0. So it'll be b over 1, which is just b. So our limit as x approaches infinity is b, and our limit as x approaches negative infinity is 0. This is pretty much all the time. That's why b is called the limiting factor. I'll tell you why. Y-intercept. What's the y-intercept? Well, our y-intercept when x equal to 0. E to the negative 0 is 0. No, it's not 0. 1b over 1 plus k times e to the 0 is b over 1 plus k. And that's our y-intercept. That's it. Right? So we're going to go to our next question, keeping these two things in mind. Right? Especially the top end behavior, the limit as x approaches infinity, and the okay, these are some functions. If you want to look over them, they're not really important, but it basically shows how functions are different. Right? This one doesn't change the y-intercept. No, this one doesn't change the like the course, but it does change the y-intercept. It doesn't change the asymptote, doesn't change the limit as x approaches infinity, but it does change the y-intercept. This one's steeper, this one's a vertical stretch, and this one's a it changes the y-intercept and it changes the asymptote. Right, so it's pretty interesting stuff. But these are just the differences. I just drew them out for you. This is the real logistic function. We have our limiting growth up here, and then if we have this graph right here, b is our limiting factor, or our limit as x approaches infinity, and this is our y-intercept. So if we graph these, right, we know our I'm not even gonna put like a negative in here. We know our y-intercept, that's 1. No, actually, we know our y-intercept is b over 1 plus k. So 1 plus k, k is just 1 here. There's no k, so it's 1/2. So let's say that's 1/2, and that's 1. So our graph will look something like this right here. Right? That's our graph. Right? That's the simplest graph you can get. So what about 2 over 1 plus 3 e to the x? So this time our limiting fact. Oh god, I'm sorry. I'm also sorry about the screaming. So our limiting factor right here is 2, right? Our limiting factor is 2, but we have 3 at the bottom, so our y-intercept will be 2 over 4, which is still 1/2. So we can draw our 1/2 right here. We can draw the 2 right here, and then our function will look something more like this. Right? Okay, that does not look like a good logistic function. I'm sorry. Or it'll look something like that. Right? That's better. So the point of symmetry, right? Because this has a point of symmetry. It's symmetrical across 1/2. You can just flip it, and then you'll get the same thing across 1/2, about 1/2. But this point of symmetry is different. It's like about right here. So when you flip it right there, it will be 1/2. But at 1/2, it's not the point of symmetry. Right? The point of symmetry is the point where it's the logistic functions reach its maximum growth, and it can't it can't grow anymore. It'll start to taper off, right? That's the point of symmetry of the function, and it's definitely not at y equals 0 here. So this is just the stuff that I've been already explaining. We'll move on to applications. So determine the formula for the population of San Francisco, and if the population of San Francisco is 300,000 and increases 1.2% every year from then, that's pretty simple. It's just 300,000 is our initial value, right? And then multiply by 1.2% every year. So we already have our initial population. We want 1.2% more, which is just this. And then our year, we could just represent that as t, and then t is time in years. And that's our function. For any exponential growth modeling, population, money plans, whatever you want, is the formula is b times 1 plus r to the t power, or k times 1 plus r to the t power. But r is our rate, so that will be increase is 1.2 or decrease is 5.8. If it's decreased, it will be minus. Our t is our time, and our b is our initial value, right? Or a, k, b. Which one you can use whatever the heck you want. This is the formula, right? Of the exponential growth. Okay. So half-life. We have half-life now. Half-life are another one of our applications. Half-life of carbon-14 is approximately 5,700 years. How many years does it take for only 1/4 of the substance to remain? We have our half-life is 5,700 years. So our half-life is every single 5,700 years you have. So that's t over 5,700. Because it only happens once every 5,700 years. It will be reduced by 1/2. Right? It will be reduced by 1/2 every single 5,700 years. Because t is, if you put 5,700 years in there, you'll have 1/2 to the 1, which is 1/2, right? So times whatever by 1/2. That's why it's called the half-life. And then it doesn't matter what's here, a. You can put a here, a times 1/2, right? So for 1/4 of the substance to remain, 1/4 is 1/2 times 1/2. So you gotta have 2 iterations of the half-life. 2 iterations. So we have 5,700 is 1 iteration, and to make it 2, you can just do you can just multiply by 2, right? So 5,700 times 2 is 11,1400 years. And that is our answer, right? 11,1400 years, right? That's just Egyptian junk. Anyways, sample is 39.8 grams of carbon-14 is stored away in an ancient brewery, where it has stayed. Brewery? What? Alchemy lab, where it has stayed for 2,550 years. And how much of the isotope is left? So we have 2,550 years and 39.8. Our initial value is 39.8, and we multiply that by 1/2 times 2,550 over 5,700, and I'm going to use a calculator right now. It will be 39.8 times 2,000, times, what is it, half? So 1/2, 0.5 to the power of 2,550 over 5,700. That'll give you 29.188 grams. So there will be 29.188 grams left. So the amount of people that can win each cash prize in the lottery is listed below. 8765432 12622. Yeah, all of this. So first question is, why did I make the X inputs in descending order? Why did I make them in descending order, not ascending order? Well, it's kind of obvious if you look at the function, but it's because the prizes get smaller and smaller, and the values get smaller and smaller, right? So when we have x as x is equal to 8, x equals to 8 means the prize should be big, right? When the prize is big, there's not many people that can get them. So the higher the chance, the lower the x amount. So to show that more people can get them. If I put them in ascending order, it still makes sense because it'll be it'll be the the higher numbers means the more common numbers, but in this case I wanted to put the higher numbers mean the more prizes, the higher prize that can be won. Find exponential. We're not doing this at all. Let's not do this. But when we graph this, we'll get a function something like this. No, wait, give me a minute. When we graph this, we'll get a function that looks something like this, right? We'll get a function that looks something like this. An 8 will probably be like right here, and then 1 will probably be like right here, right? We'll get a function something like that. So what does the area under this curve represent? What does the area under the curve represent? What is it called? So systematically, the area under the curve represents the total amount of money that can be won. Yeah, that's basically what it represents. As the prizes become infinitesimally small, as the prizes become infinitesimally small, as the amount of prizes become infinitesimally large, so it'll be like 1, 1.1, 1.2, 1.3, 1.4. We'll have an infinite amount of money. If you want to skip this, you can, because it really doesn't matter. So this area under the curve represents this the amount of money, total money that can be won. I won't say on average, but basically the total money that can be won theoretically if the amount of prizes follow this curve, right? That's the area under the curve. I'm not gonna write that down. I've set it out. So what does B represent? Well, we have A times B dx. What does the B represent? The B represents the decrease in chance for every single next prize that you can win. So for example, let's say the chance is 1/3. There is a 1/3 less chance that you can get the prize in number 4 than you can get a prize in number 3. There's a 1/3 less chance you can get a prize in 7 than you can get a prize in 6. Uh, if that B is 1/3, so there's a B less chance that you can get a prize in the number higher than it than the number than that number. So a group of students start a rumor that spreads at this rate, right? 650 over 1 plus 1,500 e to the minus x. And how many students heard the rumor in day 2 is our first question. We'll have day 2, so our unit's just 2. X equals 0 is the day it begins to spread. That's day 0. That's day 0. Don't, right? X equals 0 is day 0. So how many has heard in day 2? We'll have 650 over 1 plus 1,500 e to the power of minus 2, and that'll give us 3.18 students, which is, let's round it down, we'll have 3 students. How long does it take for 350 students to hear the rumor? We'll need a little bit of logarithmic rules to do this. We'll use it. 350 is equal to 650 over 1,500 e minus x. So we can switch the positions of these two. We'll have 1 plus 1,500 e to the minus x is equal to 650 over 350. I'm just going to simplify that into 13 over 7. That's the same thing as 650 over 350. Subtract 1, we'll have 6 over 7. 1,500 e to the minus x is equal to 6 over 7. And then we can just solve for this minus x. Divide by 1,500, so you have e to the minus x is equal to 6 over 10,500. Take the natural log, right? If you take the natural log, ln, you'll reverse the e. You'll get rid of the e. So natural log of 6 over 10,500, and it's negative, so put the negative in front, and then you'll have x. You'll have x is equal to negative the natural log of 6 over 10,500. You can simplify this function to 1 over 7,050. Natural log of 6 to the 10,500 over 10,500 is minus 7.4, minus 7.46, and it's minus, so it'll be 7.46 days, right? In day 2, only 3 students heard it, but in day 7.46, 350 students have heard it. So this growth grows pretty fast as well. It's not just the exponential. It grows fast until it gets to that middle point. So what number would change if the group students were popular? Well, let's think about it. Let's think about it for a minute. This 650, or what's our y-intercept? Our y-intercept is 650 over 1,501. That's our y-intercept, right? How would we signify a more popular group of students? If the students were more popular, by day 0, there would be more students hearing the rumor than if the students weren't popular, right? So the value that we can change to make those students more popular is this value right here, 1,500. If we take this 1,500 lower down to 50 or something, then we'll have 13 students already hearing the rumor at day 1, right? If you lower this down to 50, it'll be 650 over 51. There's about 13 students already hearing the rumor by day 1. It's just day 1. 13 students already heard it because you're popular, you know? And it's cool that you're popular. So this number would change if the students were popular. Maybe this number would get larger as well. If this number gets larger, you'll be starting to spread it into alternate schools, other communities. This number would get bigger, but this number would get smaller if it's just your school, right? That's basically what I'm trying to say. So we're gonna find the logistic functions for the following now. Let's draw some graphs. So we have our initial value. Our initial value for the logistic function is the same as our initial value for the logarithmic function. We have 10, and then we have our growth limit as 50, right? That's y equals 50. So it looks something like this. I honestly don't care about my bad graphs anymore. But it passes through 2, 40. So we can just put our y is equal to our growth limit's 50, so 50 over, and then initial value is 10. So our initial value is 10, so we have to have a times b to a times b to the x, a times b to the x, right? Basically, our initial value is 10. This actually, no, there's no a right here. It's just 1. 1 times kb to the x. And then this, 1 plus. I'm really sorry. I lost all my brain cells over this question. So our b is 0. Our x is 0. So our b is going to be 1. So our y-intercept is 50 over 1 plus k. But our initial value is 10. So we can automatically figure out our k. So this is equal to 10. We can solve for it, or we can just look, right? 50 is equal to 10 plus 10k. We could just look and notice k is equal to 4. And that's it. We're good. K is equal to 4. But it passes through 2, 40. So we're going to put this 2 here, and we're going to put this 40 here. Now we have 40 is equal to 50 over 1 plus 4b to the b squared, right? Because it passes through 2. You know, I'm not going to do this question because it takes too much space. I've crammed everything into one review, and it's not fun. So I'll let you solve this function, and I'm going to tell you the answer. I'm going to work it through really quickly. Right? Pause it if you want to solve this question. I'm going to solve through it right now. Okay, did you get it right? Because if you got it right, the function that you would get is 1 over 4. B is equal to 1 over 4. So our final function is y is equal to 50 over 1 plus 4 times 1 over 4 to the n. I'm not sure if I actually did that right. 50 over 4 is 5 over 4. Subtract 1 is 1 over 4. Yeah, it's correct. Our b will be 1 over 4. B squared is 1 over 16. It can't be negative because if it's negative, it would be reflected the other way. So it doesn't work that way. It's 50 over 1 plus 4 times 1 over 4 to the n. Okay, we are going to go through to logarithmic functions now. So what's a logarithmic function? A logarithmic function is the inverse of the exponential. We want to get rid of something. If we had, let's say 2 to the x, right, equals 4. You just know that this 2 to the x is just equal to 2 squared. X equals 2. Simple function, right? We have our previous ways of solving our functions, like x to the 5th is equal to 243. When the exponent is known, we can just take the 5th root of both sides. But now if we have 5 to the x is 243, there's no way to do this. There's absolutely no way to actually do this without using the calculator and like approximating things, right? Approximating. But now we actually do have a way, and that way is called logarithms. All right. We get rid of the 3 in this case, so we take log base 3. Right. This is what I would normally write, but you can't actually put this in the calculator. So what's log base 3 of 9? Log base 3 of 9 is log base 3 of 3 squared. And log base 3 of 3 is, but these are inverse of each other, so 3 to the x and log base 3 of x. So these are inverse to each other, and whenever they're inverse, it's always going to be 1. And we have this property where we can just put 2 at the bottom right here. Log base 3 of 9 is basically asking 3 to the what power is 9, right? The answer is 3 to the what power is 9, so x is just equal to 2, so this is 2. 1/2 to the what power is 4. Well, you take log base 1/2. We're going to do calculator friendly moves now. So we're just going to put ln right here. And when we put ln, we can put x in front because of a property that I'll explain to you why it works. ln 4 over ln of 1/2 is equal to x, and then if you put this in a calculator, you'll get x is equal to minus 2, right? Because it makes sense. 1 over what's 1/2 over minus 1? That's 2. 2 squared is 4. So 1/2 to the x gets you 4. You have to put x equals minus 2. E to the x equals 2. What's x? Well, take ln of both sides. Ln is the canceller of e. Ln cancels e. Right? So e and ln is just gone. So x is equal to ln 2, which is roughly 0.693. 5 to the x is equal to 12. What do? You can take ln of both sides again. X goes in front because of a property I'll tell you later. Divide by ln 5. You'll have x is equal to ln 12 over ln 5. And that's our answer. Okay. So, oh god, I'm sorry, I'm skipping so many slides. So the logarithm is the inverse of the exponential. Here's a graphical representation. This is e to the x, and this is ln x. See? E to the x, ln x. It follows all domain, all range rules. Domain of e to the x, what's the domain of e to the x? It's infinity. What's the range of ln x? It's infinity. What's the range of e to the x? 0 to infinity. What's the domain, what's the domain of of ln x? 0 to infinity. So domain and range is the same. Domain of the inverse is the same as the range of the actual function and vice versa, right? So if ln x is equal to 5, solve for x. Well, if we have ln x equal to 5, we can just take the inverse, right? Like how you, whenever you have x plus 3 is 8, you subtract 3, take the inverse. So you take e, both sides, x is equal to e to the 5, which is a big number, pretty big number. etx equals 2, what's ln x? etx equal to, you take ln on both sides, you have x equal to ln 2. So what's ln of x? ln of x is equal to ln of ln 2. And that's our answer. If x is equal to 2, express x in terms of e to the x. This sounds a little bit confusing, but basically, if x is equal to 2, right, what's e to the x? What's e to the x? So if we take e to the x on both sides, now we have e to the x is equal to e to the 2, but we don't actually want e to the x, we just want to express this x. So we have to take the L. Okay, no, you know what? This is the wrong way to solve this. This is not the right way to solve this. If x is equal to 2, express x in terms of e to the x. So we have e to the x is equal to 2, right? E to the x is equal to 2. So we have to take the ln of both sides, and then we have x equal to ln 2. So when x equals to 2, e to the ln 2 is equal to 2. And that is that's basically what our what I wanted to say. E to the ln 2 is our is what I wanted to get, right? So if x is equal to just any number, it'll be e to the ln x is equal to x, right? That's what I wanted to say. It's a really confusing question. I don't even know why I read. Oh, blank page. So the logarithm base of a number is the inverse of the exponential base of that number. So if we have 2 to the x is equal to 8, log base 2 of 2 to the x is log base 2 of 8. And we have this x equal to 3 right here. So x is equal to log base 2 of 8 is equal to 3. I'm going to write something right here that's really important. If a to the x is equal to b, then log base a of b is x. This is one of the most important things that you have to know if you want to prove anything, if you want to do anything with logarithm. If a to the x is equal to b, then log base a of b is equal to x, right? Or ln b over ln a. That's also equal to x, right? That works as well. Or log b, log a. So evaluate log base 3 of 27. What's 27? 27 is 3 cubed. So log base 3 of 3 cubed is 3. Log base a of a cubed is 3. Because a to the x is equal to b. So a cubed is equal to b. So log base a of a is equal to 3, right? A cubed is equal to a. So log base a of a is equal to 3. Log base 1/2 of 2. What's log base 1/2 of 2? Well, 2, how do you turn 2 to 1/2? You take the negative exponent, so you get -1. That's it. Log base 8 of 8, square root of 8. 8 is 8 to the 1. Square root of 8 is 8 to the 1/2. Add 1 and 1/2 together, you'll get 1 plus 1/2 is 3/2. 8 log base 8 to the 8 to the 3/2 is 3/2. Log 10 plus log 100. What's log 10? This log right here is called the common log, and the common log is just log base 10, right? Log base 10 of 10 is 1. Log base 10 of 100 is not 10. It's not 10. It's 2, because 10 squared is equal to 100. So 2 and 1 plus 2 is 3. Log base 5 125. Log base 5 cubed, so this is 3, minus log base 5 1 over 25. 1 over 25 is 1 over 5 squared, which is 5 negative 2, 5 to the negative 2. So log base 5 of 5 to the negative 2 is minus 2. 3 minus 2, that's fine. Here's some proofs of the properties of logs. We already know this property just from the inverse property. Log base A of A to the B is B. This is how you prove that log base A of B to the C is C log base A of B. And that's why I was able to take these, when I did ln of 3 to the A, or ln of 3 to the whatever, I could take the A in front and put ln3. When I solved ln3 to the x, you could take ln3 to the x, you could take the x in front, ln3. And this is the reason why, right? You take this, you put it back into this form, this exponential form, you modify it a little bit, take the c root, or take 1 over c both sides, you move it back to this form, the logarithmic form, and then you multiply by c on both sides, and then you'll get c times log base a to b is equal to n. Oh, blank page. So these are another property. These are all the other properties of log. So when you have log base a, log the same base a plus log the same base b, you'll get log of ab. I'm gonna signify the same base right here. I'm gonna need to change it to a different color. Log base n, log base n, log base. They have to be the same base, right? And this is the reason why. We'll take two examples. Log 10 to the third times 10 squared is equal to 10 to the fifth. 10 to the 3 plus 2 is fifth. This, and then you could use this property right here already to get the same thing as this. 3 log base 10 plus 2 log base 10 is equal to log base 10 to the fifth. So log base 10 to the third plus log base 10 to the second equals log base 10 to the fifth. And then we've already proved that 10 cubed times 10 squared is 10 to the fifth. So this is the reason why, using the two properties that I've already explained. And the subtraction works for the same reason. I don't want to show the proof again. But this rule is a little bit more interesting right here. It's called the change of base rule. And the change of base rule is, I could say log base 8 of 16, and I could give it a different base. I've been giving them ln's, so I could just give them a totally different base. ln, this is log base e, right? ln is log base e. So if you haven't already figured that out from the inverse, ln is log base e. So ln of 16 over ln of 8 is the exact same thing as log base 8 of 16. Here's why. Log base 8 of b is equal to this, right? We'll assume that it works. So if we set this b is equal to a to the k, right? Because any number can be written in another base with an exponent, right? So for example, 4 is 2 squared, 3 is 2 to the log base 2 of 3, right? 3 is 2 to the log base 2 of 3. It can be written in any exponent, but all numbers can be written in another number to a power, so we can replace all the b's to a to the k, a to the k, a to the k, right? Log base 8 of a is just 1. K, you move in front, you'll have k is log base a of a, that's k. And then this k you can also move in front because of the rule where you can take the power and then you move that in front. It's called the power rule, I think. So we have k is equal to k log base c of a over log base c of a. Log base c of a over log base c of a, that's just 1. So k is equal to k is equal to k. Proven, right? It's a proof, not really a derivation. I can't really derive this, but I can prove it, and that's the proof, right? So there you go. And then we have, I think we're gonna need to separate this into two different videos. Use properties of log to expand these functions. Log of 36 over 49 is equal to, well, that's, you can actually just notice 36 is 6 squared over 7 squared, and then this is log. So log, I'm just writing LG because I'm that dumb. Whenever you're dividing inside of a function using this rule right here, log base a minus log base b is log base a, you can subtract them. So you have log 6 squared minus log 7 squared. Take 2 in front, you have 2, oh god, I'm sorry, 2 log base 6, subtract 2 log base 7. That's how you expand it. Log base 4 of 25 is log base 4 of 5 squared. think I just got lazy. And then you can take 2, you put them in the beginning, you have 2 log base 4. It is a log base 4, so you could also expand it an extra step and do this. 2 ln 5 over ln 4 because of the change of base rule. So use properties of logs now to condense these functions. We have log base 8 of 16 plus log base 8 of 32 minus log base 4 of 1/2. Log base 8 of 16 is, we don't know that yet. What's log base 8 of 32? We don't know that either. So we can multiply them. 16 times 32, that's 512. Log base 8 of 512. Hey, we do know what log base 8 of 512 is. Log base 8 of 512 is a really simple, nice function. It's a really simple, nice number. It's just 3. Log base 4 of 1/2. What's log base 4 of 1/2? 1/2. If you take that to the negative 1 power, you get 2. So if you take it to the negative 2 power, you'll get 4. Therefore, it's just negative 2, which is 5. Right? So that's negative 2, and that's 512. Right? That's log base 8 of 512. Log base 8 of 8 to the square root of 2, using our properties. This is just square root of 2. Minus, we have these two, again, log base 6 of 18, plus log base 6 of 12, we can combine them. We have log base 6 of 216, multiply them, and 216 6 cubed, so it's just 3. There you go. Log base 4 of 6 over log base 4 of 36. This is pretty interesting, but basically 36 is just 6 squared. And we can use another one of our rules. Put the 2 in the beginning. You'll have log base 4 of 6 over log base 4 to log base 4 of 6. You can cancel that. You'll have 1/2. Right, so this just succumbs to 1/2. Minus log base 5 of 4 squared plus log base 5 of 2 to the 10. So they're both equal, so to multiply them together, you'll get 4 squared is 2 to the 4th. 2 to the 4th times 2 to the 10 is 2 to the 14. So you have log base 5 of 2 to the 14. And that's our final answer for that. 3 ln of x cubed y plus 2 ln of yz squared minus 1/2 ln of x8, y6, and z to the 4th. This looks like a lot, but basically all the coefficients that you have, just put them out to the front. You have ln of x cubed y all to the 3rd plus ln of yz squared all to the 2nd minus 1/2. Okay, actually, we're going to put the 1/2 in front as well. Minus ln of x8, y6, z4, the 1/2. Apply the exponents. We'll have, this is x to the 9, y to the 3rd. This is yz squared, right? Yz squared, so y squared, z to the 4th. And then this is, apply 1/2, so x to the 4th, y to the 3rd, z squared. Right, so we have these x9, y3 plus y2, z4 plus minus x4, y3, z2. But they are in natural log, so you can add them. When you add them, you multiply them, so you add the exponents. You subtract these, so you subtract the exponents. So we only have x to the 9 right here. X to the 9, x to the 4. What's x to the 9? What's 9 minus 4? It's 5. So we have ln. Our final answer is ln. And it's not even visible because I put way too many questions in here. I'm so stupid. Ln of x to the 5. And then our y to the 3rd plus y squared. So that's 3 plus 2. that's 5, and then minus 3, right? Because it's minus, so you can multiply and divide. Y squared, and then z to the 4th minus z squared, so z squared. That's it. That's our final function. I never want to do that again. Evaluate with a calculator. Thank God. Let's do it. Let's evaluate with a calculator. So ln6 is 1.79. Right? Just press the ln button on your calculator. 3 ln 5, 4.82. Log 140. 2.1. ln6 to the ln 7th power. 3.11. Log base 6 of 7, we can use the change of base rule to do this. Right? Because there's no ln6, there's no base 6 in our actual function. So it's 1.086 roughly. And then this is the same thing, change of base. And then add change of base. Right? And that'll give you 2.75, 2.754. And that's it. That was the simplest ever. So there's another property right here. This is kind of intuitive, but it's also kind of weird. But log base a to the b power. So if our base is a to the b power, to the c is log base c is log base a to the c power 1 over b. So log base 1/2 of x squared is log base 2 to the minus 1 power of x squared. Right? And this is log base 2 to the x 2 over minus 1, which is log base 2 to the x of minus 2, right? And that's our function. Or we can just put minus 2 log base 2 of x. Log base 1/6 of 2, same thing. Log base 6 minus 1 of 2, which is log base 6 of minus of 1/2, right? Log base 6 of 1/2. And if we subtract that by log base 6 of 1/3, we'd have this is equal to log base 6. I think I made a mistake again. I made a mistake yet again. Log base 6 of 1/2 minus log base 6 of 1/3 is log base 6 of 1/2 over 1/3, which is just, this is just equal to log base 6 of 3/2. I was planning for it to be 1/6, but I guess it just doesn't have to work that way. It's supposed to be a plus. Oh, okay. I think I'm going to stop there. There's no way I'm going to be able to finish this whole review in one sitting. I'll post this as part 1. So part 1 is done. This is, I think, 1.3.1 to 3.4. Next part will be shorter. Thank you for watching. I really need to get less questions in here and more understanding. But the questions, I hope they help. They were really sloppy because I put them so close to each other because I'm so stupid. But that's what it's going to be. So hope you enjoyed my rambling, and I'll see you next time.